As I just said at the very last minute of the previous hour, the how big that I'm going to be and how it's going to be handled in the computer programs is not that easy. And in order to remedy that problem, another method is actually proposed, which is called the two-phase simplex method. The main idea is again the same. The very first steps, the including of the artificial variables, are still the same. This time, just the motivation to kick the artificial variables out of the basis is a different manner. So we again have, this is the same example we solved with the big M method. Okay, I have a slack variable for the first constraint. I do not have. I have a slack variable, but I do not have unit vectors for the second and third constraints. I add my second and third constraint to artificial variables. This is exactly the same thing we did in the big M method. Yeah. And then we had here row 0 with large coefficients, all those artificials. The two-phase method is an alternative. So if we don't want to use those big artificials, what can we do is, we're creating an artificial problem. We just forget about the original objective function. Remember, my original objective function was this. But for the time being, that's why it's called two-phase. So we're going to solve the problem in two phases. In the first phase, we are just looking for a feasible solution. We don't care if the original problem is unbounded, alternative, whatever. We just try to find a legitimate feasible solution. So what we do is we create a new problem with a new objective function. Okay, the problem, the AX equals to B is the same. I still have the same constraint set as I did in the big M method, right? But this time, my objective function is different. I will just minimize the summation of those two objective functions. It's again the same. The simplex will try to get rid of these artificials to make them 0, because since everybody is non-negative, the best thing that can happen is their values to become 0. So while optimizing, simplex will try to put those artificials to 0. So I don't need to bother with big M's. I will just solve a problem. This is phase 1 then. All right, this is phase 1. So I will first solve an optimization problem with a new objective function. I don't care what the original objective function was for phase 1. I just put my artificials and here's my phase 1. Okay, this part is exactly the same as it was in the big M, but the objective function is different. Row 0. I don't have anyone else, but I have only the artificials in my row 0. Remember, these are for my basic variables, so these guys have to be 0. I do not want non-zero entries in row 0. So what we're supposed to do, we again have to do elementary row operations so that these -1s becomes a 0. So this is, we put -1 and we put -1. My next table, this is now a legitimate simplex table. I have identities, enough, unit vectors, 3 unit vectors, I need 3. Everybody's objective function coefficient is 0. This is a legitimate simplex table, proper, right? Now I'll do my simplex iteration. So be careful though, I continued as if it was a minimization problem. So most positive will enter, which is x2, because in here, most positive is entering. Since I continued, I didn't convert it to maximization problem. I continued with as if it's a minimization. So most positive is entering. I do my ratio test. A2 is the winner. So x2 enters and A2 leaves my basis. All right? Now I have to do elementary row operations so that I get a 0, 0, 1, 0 in here, right? That was the simplex iteration. I do the iteration. Now A2 is out of the basis. I can again get rid of it. I don't need to update its column so that my life is easier. Now, most positive is X1. Be careful, there are no M's or anything, so they're just numbers that we already used. So X1 is entering. If you do the ratio test, A3 is the winner, so A3 will be our living variable. X1 enters, A3 leaves. So I need a 0, 0, 0, 1 for here because that's what its column gonna replace. And here is my next simplex table. Okay, now you have to halt a little bit because the simplex says stop optimum. Now, what optimum, right? This is optimum for phase 1. I didn't have my original objective function coefficients in here. I don't know yet. Somebody wants to say something, if I'm not mistaken, because it's clicking. Any questions? Because I guess something. Any questions? Raise your hand. No question? All right. Okay. Can everybody follow? At least somebody tell me that. Is everything fine as if it was?
It's perfect.
Thank you, Oya. Thank you. Okay, let's go on then. Apparently, I need you all the time there. All right, let's go on then. So remember, this was our original problem. We converted that to here. So, all right, our phase 1, hold on, let me go back here. Our phase 1 stopped saying that phase 1 is optimal. Okay, phase 1's objective function was minimization of these two guys. They're out of the basis, they become non-basic. So my objective function value is 0, right? But this is not my legitimate objective. I forgot what my original objective was for the sake of phase 1, for the sake of getting a feasible solution. Now we are ready to go on. So we're going to bring back our original objective function, which becomes like this in its row 0, and we'll put it in our simplex table. Because now I do have this identity, right? That's what you need to start with. I do have an enough identity matrix, right? So apparently, I just know that S1, X2, and X1 altogether will give me a starting basic feasible solution. And that was how its simplex table gonna look like, right? I just don't know what's gonna happen in row 0 because I didn't perform with the correct row 0 for those all iterations. I need to get back my original objective and make it a proper row 0. That's all you do. So you bring your original objective function back in your row 0. Now, apparently, this guy is a basic variable, so I need a 0 in here. This guy is a basic variable, I need a 0 in there. S1 is a basic variable, it already has a 0, so I don't need to do anything else for that, right? So I have to convert this to 0, which means -2 of this row, and I need to convert this to 0, which is -3 of this row. You just do those elementary operations. Here it is. Now you have a proper row 0 too. Because now be very careful. I'm going to repeat myself. Phase 1 utilize the original problem's constraints, but forget about the original objective function. Because for the sake of phase 1, our only motivation is getting rid of the artificial variables, kicking them out from the basis. Now, phase 1 stopped saying that my problem is optimal. Phase 1 was optimal. The artificials were out. Okay? So after phase 1, I get the correct simplex table in the underneath. But my row 0 was not correct because all these iterations did not continue with my original objective function. All right? So you have to put back your original objective function and do the iterations that you're supposed to do if you were carrying them with you, right? Which is getting them to 0. That's what we did in here. Now this is a legitimate simplex table. And okay, when you look at it, this is the same example that we did in BChem. Again, you look at your row 0. There is no negative entry. That means nobody wants to enter. So your problem, your original problem, is optimal with this solution that's given to you. Any questions before I go to the second example? Crystal clear there, right? The idea is the same. Again, I'm creating enough artificial variables. Just instead of carrying the original objective function and putting a very large coefficients for artificials, this time we forgot what the original objective function was, and we just solve for artificials at phase one. Phase one stops when all artificials are out of the basis. Well, phase one stops when the first problem is optimized via simplex, okay? The output of phase one will tell me if I can go on to phase two or not. In this example, now, this is the table where phase one stopped, okay? Phase one says, hold on. Yeah, this is where phase one stopped. Every artificial is out of the basis. My objective function is 0. Phase one has fulfilled its duties. The artificials are out. Now, phase one, the problem says, okay, continue to phase two because this is 0. If this was not 0, we will discuss what the problem was, okay? Then we created the problem for phase two, which is this, because you have to convert the row 0 coefficients. Then you start your phase two while changing the row 0. During the starting, you stop immediately because the output of phase one, the BFS for phase one, apparently happened to be the optimum solution for the original problem. Okay? Any questions? Then we go to the second problem that we discussed. Remember, BGAM stopped saying that this was unbounded, and we have to be careful in deducing that result, and we figured that actually the original problem was infeasible, even though simplex stopped saying that the problem is unbounded because the fake problem was unbounded, the artificial problem was unbounded. All right? Now we continue then. Okay. How do we do with the two-phase? Let's solve the same example with two-phase. It's again converted to standard form. We again need two artificials, one in here and another one in there, right? That's what's happening. Phase one says minimize their summation so the summation of the artificial variables is the objective function of phase one. That's what we do. Convert it. It is convert to simplex table. This is the same. These are not required. Change them to 0, right? Make them appropriate simplex table by continuing converting these guys to 0. Now I have a legitimate simplex table to start with. This is my simplex table, but be careful. I didn't convert my minimization problem to maximization problem. I'm approaching to this problem as a minimization problem. So I'm looking for most positive entry to enter to my simplex table iterations. As you see, there is none, right? There is no such thing. I made a proper simplex table for a minimization problem. And for a minimization problem, this is optimal. All row 0 coefficients are negative. I'm done. I don't need to do anything. So phase one stops saying that phase one is optimal. All right, phase one is optimal, but my artificials are still there. So the rule to go from phase one to phase two was if this guy is 0. It's not. I still have my artificials there. And we know why, because we solved the same problem with big M. We know that this problem is infeasible. So two-phase also says the same thing. The phase one tried to kick the artificial variables out of the basis, but it was no hope, it couldn't. Apparently, the original problem is infeasible. Any questions? Is it clear? One thing I want to make sure is that in the two-phase algorithm, the very first step is searching a feasible solution. All right. So phase one always finds something, always stops with an optimum solution. Well, if that optimum is 0, I'm fine. If not, I'm infeasible. That's all. From phase one, I can't deduct anything else because I'm minimizing A1 plus A2. Both are actually non-negative variables, right? So minimizing, so I could never get unbounded in here. It can never be unbounded, all right? It will be feasible. Well, it will be optimal because my artificial problem is already feasible. This artificial problem, I made it up. My artificial variable values are 1. So if you look at it, artificial variables are 1. It's a feasible solution for this artificial problem. Then we applied simplex. Apparently, those artificial variables being 1 is an optimum solution for my phase 1. Okay. But is it good enough? Can I go to phase 2? No. Because the rule to go to phase 2 is to get a feasible solution from phase 1. I couldn't. These artificials are still here. My objective function value is not 0, so I cannot go on. Phase 1 stopped with its optimality, which is actually infeasibility for my original problem. All right, let's read them from here. So, when a basic feasible solution is not readily available, we either do two-phase or begin. Okay, in the two-phase, the artificials are again added to the same constraints that you need to. All right, so again, for the constraints where you need an excess variable or equality, you need to put an artificial variable in. All right. In the phase 1, the original problem, the phase 1 problem is minimizing the sum of those artificials. Once you optimize, you complete your simplex algorithm. You can't do any further iterations. You check if your artificials are still with you or not. If artificials are still in the basis with positive values, that means your original problem is infeasible. If the artificial variables were out, that means they're non-basic variables and their values are 0, then you can continue to your phase 2. Continuing to phase 2 requires for you to put back your original objective function in, convert the row 0 to a legitimate version, and then continue with the simplex algorithms. All right? Now, phase 1 will end in one of those 3 cases. Case 1, the optimal objective function value is positive. That means I still have some artificial variables in the basis with positive values, all right? That means our original problem is infeasible. Case 2, you optimize, your phase 1 objective function value is 0, and your all artificials are out, okay? This is what happened in our first example. This is example 2. This is example 1, right? Then you got a feasible solution for your original problem. Put back your original objective function, convert it to proper form, and continue with the simplex. Good old simplex. There's another case that can happen, all right? This is case 3. That means, okay, phase 1 stopped. My objective function value is 0. But some of my basic variables are still artificial, but their values can be 0. Like degeneracy we had in the normal simplex 2, right? That means, well, simplex optimized, the objective function value is 0, and your artificial is 0. So, well, what you can actually do is do another step just to get rid of the artificial out of basis so that you have your simplex iteration. Okay, because your objective function is 0, so even though simplex treats that variable as a basic variable, you can still kick it out by putting since its right-hand side is 0, it will always be the winner variable, but you have to be careful with which variable you're replacing it with, okay? So I repeat myself, this case 3 is pretty important. I want everybody to understand it. My objective function value is 0. my artificial variable is still in my basis with a value 0, like degeneracy, okay? So this is my objective function. I have some values like 2, 5, and there's a 0 in here corresponding to an artificial variable. That means I can do one iteration, and unnecessary in terms of optimization, but I need it because I have to replace it with someone else, a legitimate variable. Since its right-hand side is 0, it will always be the living variable as long as you look which you choose the correct column to do the thingy, because it shouldn't have a negative or 0 entry so that it becomes a valid ratio test. So for any valid ratio test that this A1 will enter, it will be the winner anyway. So in this case, what you're supposed to do is pick a column so that A1 becomes a valid entry. It will be then the living variable. Is this clear? Or do you want me to reiterate over this? Okay. Apparently, no one wants to ask a question. Then I'll go on. What's happening? No, I don't want this. Okay. Once you're done, you're out of phase 1 in one of these 3 cases. Okay. Then all you need to do is you drop the columns that are required for your artificials. You don't need them anymore. You put back your original objective function. You make the row 0 legitimate, proper, with zeros at the positions that you need. All right? And then you'll utilize your original simplex algorithm. Do most negative, most positive, depending on if you're a minimization or a maximization, and you continue like that. Any question? Okay. Some more remarks. Now, why is this working? Well, because if the original was feasible, then I could get a solution when those artificial values are 0. And that could only be obtained by minimizing their summation. So that, because as I said, minimizing something, when those guys are actually both non-negative, the best that can happen is 0, right? The 0 is actually a lower bound for this problem. So if we can attain 0, fine. That means my original problem without those artificials were actually feasible. And that's why it is working. If the original problem is infeasible, then my phase 1 will never stop with a 0 value, because my phase 1 will require those artificials to get positive values to satisfy those constraints, because without them, the constraints couldn't be satisfied. That's why this method is actually pretty handy. All right? So, more remarks. As with BigM, the column for an artificial variable can always be eliminated once it's out of the basis, because an artificial variable out of the basis will not want to come back again. Okay? Both BigM and two-phase have the same sequence of pivots. Okay? The pivots we did in BigM and the pivots we performed for phase 1 is actually the same. Okay? Be careful. Phase 1 can never be unbounded. As I said, minimizing 2 positive variables can never go lower than 0. So there is always a bound 0, which is hopefully the optimum solution of phase 1, so that it will be the feasible solution for our original problem. And one other beauty of the two-phase is it doesn't have BigM, so there is no round-off errors. Do I solve it? Okay. So any questions? If not, we have a practice example that we will solve together. Any questions? Okay. Now look at this practice example. Now tell me, how many artificial variables do we need and to which constraints? The first raising hand will talk. I'll tell whoever he or she is. How many artificials do I need and to which constraints? Come on, come on. Participation grades are popping up. I have my pen and your pictures. All right, Vasik, you can talk. No, okay.
I think 2.
Yeah, which constraints do you need them?
The first and the third one.
For the first and second
the
one.
Second one. Yes.
Okay, great. Thank you, Vasik. So we need 2 artificial variables, right? But this first converts everything to equality. I convert everything to equality. If you look, I do have, now if I look like this is -4, -2, 1, 8. No, this is the objective function. No, -3. I made a mistake. Hold on. So -3, 8, -2. Then in the first constraint, I don't have E2, -1, 0, 0, 0, 1, right? This is, if I convert it, this is how it's going to look like. And it's going to be 9, 2, 1. As you see, I do have one identity. I need 2 more. Where do I need them? I need this guy and I need this guy so that I have the identity. This means I need something to the first constraint, and this means I need something to the second constraint. Okay? So you don't need to memorize to the ones with slack or without slack. All you need to do is check which unit vector do you need, and then put the artificial that corresponds to that unit vector. All right? Let's go on. So I put my 2 artificials in, and I have my slack variable, and combination of these 3 will give me my unit vector. If we go with the big M, objective is minimization. So those artificial comes with a +M constraint in the original format, not in row 0 format, okay? Because I want to minimize this, so I want these artificials to be 0. If I put them with a very large cost in the objective function, my simplex will try to eliminate them. All right. Next step is my table, right? So I have my identity columns, as you see in these 3, my corresponding to my basic variables in the correct order. Now I have to get rid of this. This needs to be a 0, and this needs to be a 0, right? How do I do that? Well, since these are 1, I'll just add +9 times this and +2 times this. That will give me zeros in the row 0. Let's see. Here it is. Now I have my appropriate simplex table. All artificial or basic variables have 0 in the row 0 coefficients. All right. This is a minimization problem. So who is entering? The first one is, I'm looking at my participants. Raise your hands. Which variable is entering? Which variable is entering? Come on. Simplex. Simge, can you say which variable is entering? You told me that you would unmute yourselves. You need me? Okay. Yes,
x2 because its coefficient is bigger than x1.
Exactly. X2 has the most positive coefficient. So this time X2 will enter. And let's, who is leaving? How many options do I have in the ratio test? It doesn't have to be you, Simge. The very first one who raised your hand is?
3.
Gülin. Can you unmute yourself or do you need me? Yes, Gülin. Which variable is leaving?
A2.
A2, because, and I only have how many options?
This is the only option.
This is the only option because these guys are not valid. They don't even enter the ratio test. So this is my pivot entry, right? Good. Okay. Next iteration. Then X2 enters, A2 lives. I can go 1. So everything is going to be divided by 8. So this becomes 1. Everybody else becomes 0. here is my second table. Since A2 is out of the basis, as you see, I don't carry its column anymore. All right? Now, who is entering? There is only one option because this is a negative entry, definitely. So X1 is entering. And due to the ratio test, A1 is leaving. If we do the iterations, this is where we stopped. Again, artificials are out of the basis. I have X1, X2, and S3 in my basis. And this is my optimum solution with optimal objective function value. Any questions? If not, we're going to solve the same example with two-phase. Okay. All right. Here it is then. Now we're solving the same example with two-phase. Phase one is minimization of the artificials. So we minimize A1 plus A2 because we only need two artificial variables. This is the simplex table for that. I again need zeros in here. All right. So I have to convert these two. So plus 9 and plus 2. Plus 9 and plus 2, right? If you do those iterations, this is your simplex table. As remember, in the big M method, in the very first iteration, X2 was entering. Exactly the same thing is happening here. We go in the very first iteration, X2 was entering, and A2 was leaving. Let's see what's going to happen in this one. Again, X2 is entering and A2 is leaving because I told you until phase one is over, the iterations are the same. So X2 is entering, A2 is leaving. We perform the iteration. This is what happens. Again, now X1 is entering, A1 is leaving, right? And this is the table. Phase one finished. X1 is entering, A1 is leaving. Phase one finished, but unfortunately, phase one, this is not 13 because this is the original object, row 0. There was another iteration here where it says 0. Then apparently this put the original objective function in and performed the iterations, okay? We already have gone over those. So phase one stopped with this, but with 0 in the right-hand side. Now you put back the original objective function in, perform the iteration so that they have zeros in the row 0 coefficient. Then your row 0 will be like this. Again, it's optimal with value 13. Any questions? Here it is. Somehow the columns are missing. All right. So this is where phase one stopped. You put back the original objective, you perform the iterations, and this is where you get the optimum solution. All right? Any questions? Because this finishes the starting basic feasible solution topic. Any questions? Is it clear? All right. Then I'm switching to another topic, which is simplex in matrix notation. Where is it? It's not. Here it is. I may need my board this time. Okay, let me grab a glass of water. I'm asking again, any questions about simplex? Because now I'm going to matrix, a little bit algebra, and we're going to drive some things in here. From the notes, then we're done with simplex, and now we're simplex tableau in matrix notation. And this will be followed by the duality theory. Okay? Does anybody have any questions before I switch to this new, very important topic, though? I'm hoping you have your notebooks next to you because you may need to write some of them because I really like, there is a question from Gökçe. Gökçe, can you unmute yourself?
Yes.
Okay.
Could you give an example to two-phase simplex where w is equal to 0, but an artificial doesn't leave the basis?
Mm-hmm. Yeah, well,
Could
it's
you give
not.
an example?
It will be, well, I cannot make it up from my mind right now. I can only tell you that, let's say, your rows, your space, say this is A1 and X2. I'm just trying, and this is say S3. What I was trying to say is this is 0, this is 0, but still in the basis. And these are like 2 and 5, something like that. And here it was a minimization, so everybody is with minuses. Let's say X1, X2, S3, A1. And here this is the minimization, so everybody is a negative entry in here, all right? I need some more. X2, it should be 0. S3 should be 0, and A1 is 0. Okay, so this is it. Simplex, stop like that. Okay? Now, since this is 0, but it is still in the basis, this means that my original problem is actually feasible. I just don't know it yet. All you need to do is you have to enter X1, because even though it doesn't have to, X1 can still. The issue here is, now you look at the columns of X1, okay? Because this is 0, if A1 enters to the ratio test, it will always be the winning variable. All right. So you look, it has to have a 1 in here. So let's say this guy has a 2, this guy has a, 8. All right. If you look 0 over 1, so A1 will leave and X1 will enter. If I had additionals in here, let's say I put some more S2 in here, A2 in here with other coefficients like -1, -5, you should check their columns too, because as long as you find such a legitimate column where the coefficient of A1 is a valid entry, that variable should be the entering variable. Because you just want this guy to leave the basis so that you have a pivot entry and perform the iterations. Is it clear? Any questions?
Yes.
Okay, thank you. Thank you, Gökçe. Any other questions? While I'm deleting my board. Okay. Gökçe, your hand is still raised, but do you still have a question? If not, please lower your hand. Okay, thank you. New topic then, simplex table in matrix notation. You have learned to do all the iterations of simplex, all the tricks of it, the degeneracy, alternative, unbounded, how to start it, right? But now I'm going to show you something else I really like about simplex. Remember, this is what we're trying to solve, right? We're trying to maximize the x subject to ax equals to b, x non-negative. This is the system of equations I'm trying to solve. So, all right, what is a feasible solution? Any x that satisfies these constraints, right? And just look at here, this is how, in the open form, this is my matrix A, and this is my row vector C, this is my column vector X, and it's like that. Now, be careful. I have in the system m equations and n unknown. Yeah? From linear algebra, this usually ends it with infinitely many solutions. That's why, and those are all our feasible solutions, right? All the feasible space that we're talking about, any x that satisfies this condition. And as I said, since we have many unknowns than our equations, we have zillions of solutions. The ones that we're interested in are the ones that maximizes our objective function. Now, what we do is we partition our variables. That was the trick that we used, right? Now, as still, I'm trying to maximize z equals cx subject to ax equals b, x non-negative. Yeah? This with the system. Okay, what I can do is, if I had m and m equations and m unknowns, I would just solve it. It will have only one solution. One feasible solution would have to go to one optimal solution if it exists, right? But the reason is, so what? That's the idea of all these basic feasible solution thingy. What we're going to do, we select the n minus m variables. All right, we set them to 0. Then my remaining variables can be solvable if the matrix representing them is invertible. That is the whole trick in this basic feasible solution idea. We select n minus 1 of them. We set these guys to 0 so that the remaining m variables will have m equations. And if that b remain corresponding to them is invertible, that means I got a basic feasible solution. Otherwise, I don't get a feasible solution. The n minus 1, n minus m variables I choose for these non-basics were not correct. Pick another one. Okay? That is the whole idea under the simplex algorithm, under the basic solution, basic feasible solution. So because we have more variables than our equations, we just select those more variables, some of them, enough of them, set them to 0 so that we could solve for the remainings. Each such solution will correspond to one of my corner points. This is just reminding you, you have already gone through these before, right? So that's what we do. We just represent then our original A matrix. We just partition our A matrix to B and N. All right, it's the same A again. You just shuffle the columns. So the ones that goes to my basic comes first, and the remaining are in the remaining columns. It's just playing with the places of those columns, right? And while according to this partition, we're partitioning the variables. We're setting some of them to 0. So according to this partition, you have to partition your x vector and your c vector too. Remember, this is how they're coming. So I played with, hold on, let me clean this up. So what you're doing is you're selecting some of these guys, you're making them basic, and the remainings are in the n minus m. So anything that you make in here should also go in here and in there because they are multiplied with the same x. So you have to play with the x vector too. That's what we're doing. We just then, instead of A, we say B and N. According to this partition, I partition my x vector to xb and xn. While this x vector multiplies the c vector too. So I have to partition my c vector too. And this is it. My original problem. Maximize cx subject to ax equals to b, x non-negative, is the same with maximizing cb, cn, xb, xn, because I just played with it. It's already written here, so I don't need to write it in here. bn, xb, xn, and that's it. All right? Okay. Now is important. So let's see what's written in here. This is my original problem, right? This is my row 0, z minus cx equals to 0. Z minus cx equals to 0. bxb plus nxn equals to b, xbxn equals to 0, because this is the same. I'm just doing the matrix algebra. This b, I just partitioned. So this is actually ax equals to b, the same thing. I'm just partitioning those x's. So that's exactly can be written like this because they're all in appropriate dimensions. I have number of m variables in my xb, and I have n minus m in my xn. And those are the columns that are left for my xn variables to multiply with. Now, if I do this, here is the trick. So let me go here, and I really want to show it like that. So I'm maximizing z minus cb, xb minus cn, xn equals to 0. I have bxb plus nxn equals to b. Now, all I'm going to do is I'm going to multiply this thingy with b minus 1 from left-hand side. Then it's going to be b minus 1 times b times xb plus b minus 1 and xn equals b minus 1 b. Now this thingy this is identity times xb plus b inverse n xn equals b inverse b, right? That's what it is. So instead of xb then, so this is, be careful what's in here. The non-basic variables, coefficients are actually b inverse n. Basic variables coefficients are identity. And in the right-hand side, I have b inverse b. This is my simplex table. Remember, we have identity. Here they are. And this is the reason. Now, what is row 0? Row 0 comes from here. So here you can easily deduct that xb equals b inverse b minus b inverse n xn. All you're supposed to do is I'm going to put this in here. If you do that, your row 0 becomes this. Because CBB, all XB thingies will go out. Instead of XB, you put this. There is no XB then. But for XN, you have CBB inverse N because XN multiplies with that. And B inverse B cancels itself. All right? And if you remember, then let's go back. So this is my B and N and B and minus CB minus CN, original simplex table. If you know your B inverse, if you know your basis, multiply everything with B inverse. I multiplied everything with B inverse underneath, and I need 0 in here. Yeah. In order to get 0 in here, you just add this CB times up. That gives you your simplex table. All right? That brings you to your legitimate simplex table. Any questions in here? This is crucial. I can re-explain any step, but we just derived the simplex table in matrix form. So if I can tell you, you know what, x1, 3, and 4 is basic. Give me the simplex table. That's what you're supposed to do. You will get B from x1, 4, 5, whatever I told you. Get the inverse, then multiply B inverse with the remaining n, and that will do the same thing. So do the math, do the algebra, and convert and construct your simplex table immediately without big M or two-phase if I tell you that these variables are actually going to be the basic variables of your simplex table. And at any iteration, you can always, like in your previous simplex tables, you could always actually convince yourselves that this is the format of the table. The only thing is, since in order to show it in a better way, we just shuffled the columns so the basic variables are in the very first columns. They're normally scattered around, but if you shuffle them, this is what you're supposed to see. Any questions? This was pretty crucial, actually. Is it clear? This is really important. Or if you ask, I can re-explain any part of it from the beginning. No questions? You all got it? Okay. This is really, really, really important, all right? Now, first of all, let me put here the thing that we just derived. We have derived the simplex table format like this. For basic variables, the row 0 coefficients are 0. I have an identity underneath them. For non-basic variables, the multiplier is minus Cn plus CBB inverse n, and there underneath is B inverse n. My right-hand side here, B inverse B in here, and I have CB B inverse B in there. This is in general. no matter what the format of your A matrix is, this is my general format. Okay. Now it says, okay, how about there was an identity in your starting, hidden in A? Because when everything has a slack variable, then your original A has an identity in it. You're always carrying it, all right? In all those iterations. So when you convert it to the simplex format, this is what you're supposed to do, yeah? Okay, let's put it in here then. So minus C. This time, be careful. I didn't partition with respect to XB and XN. I carried the original ordering of the variables. Because in here, I just shuffled the columns so that the basic variables are the first M in my table. So this says it's 3, 5, 8, then comes the rest, if my 3, 5, and 8 are my basic variables. Here, I didn't do that, all right? But the idea is always the same. It's just minus C times A goes up, and sometimes if the A has a B in it, it becomes identity. Then, the slack variables are here. My A matrix, my identity, and the row 0 coefficients is minus C and 0, right? Now, any simplex table with a B is like this. So let's see then how it's going to be if I do it in here. All I'm supposed to do is I'll multiply this part with B inverse. And there it is, right? I'm multiplying at any B iteration. That means I'm multiplying the underneath with B inverse, and I'm adding minus CB to up because that's what we have proved that how the simplex table should be driven. All right, so I'm multiplying everything with B inverse from here, and I'm adding CB times that to up. So an intermediate simplex table, there is no gain here, is like this then. Now be careful, because B inverse is important. This also tells you something else. In any simplex table, B inverse is always hidden under the starting simplex, starting basic feasible solutions. If I have started with excess, they will be hidden under its column. This is really, really, really important, because getting B inverse you would require that in duality, and this is just proving you that B inverse is hidden under the columns of the starting basic feasible solution. Oh, nice. We have an example. Any questions before I go to the example? Any questions? Be very careful. Learn, not memorize, learn how to drive this table, because that's the heart of simplex method, actually. Before that, we were always doing iteration. Yeah, you know what? This is what you're doing. All right? You're multiplying everything with B inverse and adding CB times it to the up. That's all. Those are all your simplex pivots and everything. All right? Any questions? Okay. Then I have an example that we can actually work on all together. So this case is where I can start my simplex. Yeah, there is an initial identity in it. All right. It says construct the simplex table where x1 and x2 are your basic variables. All right. Okay. What we're supposed to do, we're going to find the table. I told you don't memorize, learn. Is this. Yeah, let's put it in here because we may need that. So I don't want to drive it right now again and again, but I want you to learn how to drive it, okay? So here I have B inverse, and here I have minus Cn plus Cb B inverse, and in my right-hand side, this is Cb, B inverse B, B inverse B. CB, B inverse B. Here I have B inverse B. Here we have XB. Okay, let's now go to the example. It says with X1 and X2 as the basic variables. Okay, that means let's bring so this was my A according to the original problem. B, X, and C. It says X1 and X2. So my XB will be X1 and X2. My XN will be 3, 4, 5. The B for XB basic variables are the first two columns, 1, 1, 3, 2. And my N is my remaining columns, which are these three. All right? I need B inverse. The whole matrix requires B inverse, right? So for this B, you need to take the inverse. Well, I won't, of course, teach you how to take the inverse of a matrix, but this is the inverse of this matrix. All right? So convert to simplex table, it says. All right. Let's make I need B inverse B for right-hand side. So if you do B inverse B, it's going to be 6 and 3. So let me try. I need X1, 2, X1, X2, X3, X4. I need 5. I have 5 variables, right? Yeah. X5. I'll have a row 0. It says I want X1 in here and X2 in there. Hold on. I need to start using these things better because I need to write row 0, 2. All right. Let's put it like this. Okay. X1, X2, X3, X4, X5, and right-hand side. We have calculated right-hand side first. So B inverse B, it's going to be 6 and 3 in here. 6 and 3 in here. All right? I need CB B inverse B. That would be my here. Well, if you do the multiplication, it's 30. So this is 30 in here. All right? Go on. I need B inverse N because I need B inverse N. Oh, it's here. I need B inverse N. So you do B inverse times N, and that's what happens. So for here, I will have minus 11, 12, 2, minus 4, and 1, right? So I'll put that in. And this is my coefficients for row 0. And that's how it is then. All right? This needs one more column. This cannot be like this because 2 by 3, you need one more column. And apparently that column is 3 and 1. Let me put it in here. Correct this in your notes. There is a mistake in the slides. There needs to be another column in here. All right? When you do the because you need that when you do the multiplication. And so in here, I'm going to have 1, 0, 0, 1, and these will be 0. And the objective functions are like minus 37, minus 6 and 10. And my here is minus 11, 4, minus 2, 1, and 3 and 1. Okay? So this is my table in a lot more cleaner way written in here. All right? Now, what did I tell you a couple of minutes ago? B inverse is always hidden. B inverse is under the starting basic feasible solution. This original problem has 2 variables, slack variables, x4 and x5. So the B inverse at each iteration will be underneath x4 and x5. Let's check if it is. X4 and x5 minus 2, 1, 3, minus 1. What is our B inverse? That. So B inverse is really under there, right? I didn't do anything, but it's really there. It's always there. Is it optimal? Of course not. I have to go on with my simplex. This is a maximization problem. Most negative enter. There is only one option. This guy lives, and we go on like this. Any questions? Okay. I strongly suggest you go through this matrix notation thingy. All right. I want everybody to be confident with driving this thing. Never memorize it. Learn how to drive it. Okay. Because if you know this, you're saved. And if you have any questions, you can pop in on Tuesday or Wednesday practice sessions this week. Both Oyo and I will be conducting them as office hours. So we will open the Zooms. We will be here, but there won't be any lecturing. We will only answer questions. So Oyo will be in her sessions on Tuesday and on Wednesday afternoon, and I'll be here on Wednesday morning for my practices. I guess you could pop in any of those practices depending on your preferences. This time, it's not like the practices we did before. We're not going to go over the homework. These week practice sessions are dedicated for office hour. All right? And there is no lecture this Thursday because there is no study set. There is not going to be a quiz next Monday. So next Monday, I'll be here again talking about duality. All right? Any questions? Yes, Ali Ilhan, can you unmute yourself?
Hello. Can you share the IDs for all of the practice sessions so that we can join?
So the other practices too, is that what you mean?
Yes.
Because
exactly.
you only see your own practice session. Yeah, we'll discuss this, and if we decide it's going to happen, we will do that in the piazza.
Okay, thank you.
Okay, Didem, you want to ask something?
I can't understand the mistake part in the slides.
Here it is. Look at here, B inverse N, multiplication of B inverse N. It's a 2 by 2 matrix and 2 by 3 matrix. The result cannot be 2 by 2. The result needs to be, so there is another column in here, which is, I guess, 3 and 1. Yeah. Okay, that was the mistake in the slides. Anybody else who wants to ask another question? We still have 1 more minute, then I have to leave the room. Any question?